Oh, nice, it's recording. Okay, and I have to share my screen. Okay, great. And let me do that. Okay, so you should be able to see my screen. Excellent. Okay, so how about we start talking? We'll review a little bit about what chapter 10 was all about, or however you want to consider it, right? This section about making alcohols. And then we'll think a little bit about what we've, done before then too, leading up to now, so the past 2 weeks as well. And then we'll work on some problems, and we'll do a whole bunch of problems, right? Okay. Sound good? Yeah. All right, let's go. Here we go. Okay, so this week we talked about, well, Professor Molander talked about, right? I wasn't there. This week covered chapter 10, and I'm used to going by the book, but you can consider it workshop 11, you can consider it lectures 24, whatever, right? So this was alcohol synthesis. Okay, although that's a little bit of a misnomer. Yes, this chapter kind of or this whole section kind of talks about oh yeah, you can make alcohols this way, but there's a clear there's something that clearly matters here, something that stands out, which is the fact that we're talking about organometallics now, right? And up till this point, every single time I've always said all the time, you can't make carbon-carbon bonds. If you get to a point in a synthesis where you have to make carbon-carbon bonds, you might as well just give up. And then, okay, last week or the week before or something, we were able to make these. We were able to make these guys, right? And then, okay, this was pretty nice because then we could do SN2, or you could even do addition to carbonyls sometimes, right? You could do one of these things, right? And that's pretty cool because now we can make carbon-carbon bonds. Well, organometallics are way cooler. Okay, they could do way more stuff. So these are obsolete now. Forget about it. It's old news. You've grown up. You're past that, right? Organometallics are really what matter now. Okay, and they're important, and they're also kind of hard. So that's a kind of important thing to talk about. Anyway. Yeah, so this section talked about alcohol synthesis, and okay, I also went through and looked at the lectures, right? And it's the same thing as what it always has been, right? He writes up or whatever professor writes up a whole list of these things, and then it's okay, well, you can use them now, right? So there's a long list of these things. Keeping them in mind is can be tough because they can all do different things and they all work in different circumstances, right? So it really depends on what synthesis you're working on. But, well, why don't we make ourselves a list? We can refer back to it later, right? That way we know what different ways we have in making alcohols. All right. Let me stop talking and actually get to it. Okay. So what do we have? SN1 and SN2, right? Those are old. I mean, those are ancient, right? We've done those forever. Okay. What's something else? How else do we make alcohols? Now it's you guys.
Opening of an epoxide ring.
Oh, that's a good one. Okay, yeah. Yeah, so there's epoxide opening. Okay. And important idea with this is that you could do it either in acid or in base. Okay. And the products that you get out, depending on which one you do, will differ. Okay. So if you're doing an acidic epoxide opening, your nucleophile will go onto the more substituted side. If you're doing a basic one, it'll go onto the less substituted side. Okay. If you remember, there's this little garbage trick which my Orgo 2 professor taught me, and for some of you who have Amos Smith next semester, he'll teach you the same thing. And this is total nonsense, but you could totally do it anyway, right? So if you have this epoxide and it goes in acid, okay, right? Whoops. Here we go. Okay, so there's this thing is positive, right? And let me make this a little bit more interesting. We'll put an methyl on there, right? Okay, and the trick is well, this doesn't really happen, right? This is kind of fake, but what you could do is say okay, well, what if I just remove that bond, right? kind of like writing resonance, except you're not allowed to break single bonds in resonance, but hey, nobody's going to stop you, right? Or you could do, for example, you could also do like, let me get a different color because we're in an advanced stage. Okay, you could also do something like this and something like this, right? Okay, and this is way more stable in some like really incorrect sense, but for the sake of thought, it totally works, right? And so this is what will actually react, right? And so you could imagine taking like water, for example, right? And then doing something like this, right? Okay, cool, whatever, right? And I don't know. Sure. Okay. So you can think about doing something along those lines. Okay, cool. So epoxide opening is a great one. And in fact, it's one that people really love asking about. So I would expect to see it somewhere, right? And we're going to do some problems related to it also. Well, what else is there? There's a lot.
Hydroboration, oxidation.
Exactly. Which is Markovnikov or anti-Markovnikov? This is old, so.
Anti-Markov.
Anti.
Yeah. Hydroboration and oxidation. And this is anti-Markovnikov. Great. Okay. Right. So remember what that means. If we have something that looks like this, right? First step is to give some some thing with a boron on it, whatever they're called. I can never remember the names of them, right? And again, no points for being creative. So you could use the same reagent every time, okay? Use BH2, thiazobutyrylborane, okay? Why do you use this one? Does anybody know why this is a good choice to just always remember this one and not think of any other ones?
Is it because it's bulky?
That actually is part of it. Yes, you are. So that in part, yes, it is. There's another good reason though.
It only has one hydrogen?
Yeah, exactly. So in particular, if we want to like, whenever we use alkynes and we want to do hydroboration on them, because remember, we can have an alkyne, and then if we hydroborate, then we'll get this enol, right? And then this will tautomerize, which is very important for you to know, and you should definitely know the mechanism of it 100%. This will tautomerize, and so you'll get an aldehyde, right? And this is really useful. This is a great reaction. This is one that like should always be in our tool set, right? But to do this, you need just one hydrogen. Well, diisocyanylborane has only one hydrogen, okay? So if you remember one, this is a good choice, and you don't need to remember any others, okay?
So does like the BH3 THF thing not stop there or something?
Yes, I don't remember exactly the details. I think it will add twice though, and you generally just don't want that. Yeah, I don't know. I think it was something fairly specific. I also know that like if you have other functional groups and you have a whole bunch of hydrogens on there, I think it might start reacting in other places too, and that's not really good. Yeah. Yeah. But hey, you could also do BH3 THF dot up here. Totally fine also. Okay. Yeah. Anyway. So the point is for this one up here, right? Okay, so we pick this and then, oops, I zoomed in. Yeah, and the other step is oxidation, right? And well, I think to this point in the class, you've only really seen one oxidizing agent, or at least one thing that like you specifically use for oxidizing. in the next week or two, you'll see like a whole bunch more because the next chapters are going to talk a lot about oxidation. But here, in terms of like replacing the boron with an oxygen, you just have to use hydrogen peroxide. Right. Anyway, that's all to say. It's anti-Markovnikov. It goes on here. Okay. And what is the companion to hydroboration? What is like the one that you learn alongside it? That's Markovnikov instead.
Oxymercuration, demercuration.
Yeah, exactly. So, yeah, so the alternative is oxymercuration, demercuration, right? So that is a good choice. Anyway, yeah. Well, why don't I just draw the same one then? And well, here, don't forget your reagents. So it's mercury acetate here. And then you need water also. Okay. But, well, let's be a bit more general than that, right? You don't need just water. You need some alcohol, something with an OH on it. Water has an OH, so it works fine, right? And then second step is sodium borohydride, which you saw again this week in terms of reduction, which we'll talk about in a moment, right? But this thing goes on Markovnikov. And since I just used an alcohol, ROH, it actually makes an ether. So this could be an alcohol, but it could also be an ether. All right. And this is totally something that's worth keeping in mind because it is by far one of the easiest things to forget about. Okay. I can't tell you how many synthesis problems I've seen that have a product with like a, you know, something like something, I don't know, along like these lines, right? Where it's like tertiary on both sides, so you can't do SN2, or if you've heard the term, you can't do like a standard Williamson ether synthesis. Like in a case like this, the way to do it would actually be to do oxymercuration, demercuration. Okay. With alcohols like this. Okay. There's like no other good way to make this alcohol. And other times, oxymercuration, demercuration can just save you like 3 or 4 steps. So it's hard to keep in mind. And well, I shouldn't say that for everybody. Maybe for you, it's super easy. But I know when I was doing this, like this was one of the hardest things to remember about, because like it sneaks up on you. And it's hard to remember that this is a good way of making ethers too. So, excellent. That is also a great reaction. And it doesn't just make alcohols, it's better than that. Okay. Great. Any other thoughts about reactions that make alcohols?
Acetylides. You guys like?
Yeah. Let me actually move those even farther down, because carbonyl additions are their own class of things. Okay. And those of you who were here last week or might remember, I said like organic chemistry 2 is basically a class about carbonyl additions. All right. So like, in fact, in this alone, you're learning like most of organic chemistry 2. So you'll just be seeing a lot of the same stuff over and over again. Okay. Which is to say that now is a good time to learn it, but also, well, you'll be seeing it again over and over. So you know, you'll have plenty of time to get used to these. Okay. Yeah, and so one class of these carbonyl additions is if we have this acetylide. Right. So it'll kick that up. Right. And then, well, it depends what happens, right? So if R is a bad leaving group, well, then you could just give it some acid and, well, exactly like you said, look at that. That's a nice compound, right? Tertiary alcohols they're kind of hard to make otherwise, so this is a good way of doing it, right? But if we could kick R off, well, let me pick a different color. Oh yeah, excellent, right? Well, then we can get a whole ketone, which is like extra nice, right? Yeah. And then there's a whole bunch of subtleties about like, well, could you add another one, right? Which is a lot of what this stuff about organometallics is all about, right? That's kind of where a lot of this discussion comes in. Yeah. So, okay, good. So we've seen adding acetylides, and we've kind of worked with that, right? That was kind of our pre-organometallic, if you want to say. Yeah. And then I guess there's a couple more that I've seen come up, and well, you could include these two, right? So there are dihydroxylations, right? What's one of the ways that you could dihydroxylate?
Cold dilute potassium permanganate.
That is a good choice. There's another one. What else?
OS.
Cationic OSO4 and H2O2.
Yep. Yeah, both good options, perfectly fine. Use either one. Again, you don't need to be creative. You just need to know one. At least I should say that applies to when you're doing syntheses, right? There are a bunch of predict the product reactions or questions where, you should be familiar with what different reactants you can use. But in terms of like using them, you just need to pick one. So, yep. Yeah. Any other thoughts about what you could do here? A few more, but less interesting.
You could use a halohydrin reaction.
Yeah. So that's another option, right? So you could do a halohydrin reaction, right? So if you have this double bond and then you add bromine, right? Without going through all the steps of the mechanism, you get this bromium ion, okay? And then, well, from there, pop, and you could deprotonate and get there, right? So kind of specific, but it'll get you there, right? Or at least it'll get you an alcohol, and then you got to deal with that bromine. But sometimes you want that bromine, so we do that. Yeah. Any other thoughts? Yeah. Any other old reactions that we've seen? I could not hear.
Maybe acid catalyzed hydration, the opposite of dehydration.
Yeah, thank you. That was the last one that I was thinking of, at least. So hydration, okay? And this is one that back in the day I tried to really like etch into your brain. E2 is reversible, right? So with E2, you need concentrated sulfuric acid. If you want to do hydration, well, you could do dilute sulfuric acid. Why don't we prefer hydration though? Right? This is Markovnikov. But why don't we like this reaction so much?
Doesn't it give mixtures?
Oh, I was gonna
How-
say it was gonna arrange. Like it can rearrange because of carbocation forms.
That's what I was thinking. Yeah, it probably will also give a bit of mixtures too, because it's not going to be perfectly selective, or at least not as selective as like oxymercuration, right? But
So
this
I have
could,
a question about like about this reaction because it's like not like as like or like because you can have rearrangements during synthesis. Is it just like better if we use oxymercuration?
yeah, it is. You can, so this reaction would work like to get a good product. The thing is that like it's really easy to miss when there might be a rearrangement, especially if you're doing your own synthesis, that it's better to just consistently go with like oxymercuration, demercuration. Yeah, it's just because like if you do miss a rearrangement, like that's gonna really come back to bite you. Yeah, so it'll be better to just stick with these guys up here. Although, well, these are some extras that we've seen in the past. Okay. Yeah, so we have these carbonyl additions. These are new. These are the new things that we're working on. I guess maybe I'll actually point out that there is a new way that you can do it, and let me go and move all this stuff down. Yeah, so there is a new way that you learned to, oh wait, sorry. Okay. Yeah, so there's a new way that you learned how to make alcohols as well, which was, and I had mentioned this, oh no, it's not gonna let me write, that's kind of annoying. Sorry. I can fix this one though. Yeah, there we go, okay. Yeah, so you did learn a new one, which is reductions, right? And well, you've already seen the reagents for this, at least the sodium borohydride, because we've used it before when we do hydroboration and oh no, sorry, we've used it when we do oxymercuration and then demercuration. It's the second step, right? So when we're doing reductions, well, we're taking, for example, our ketone, or in general, our carbonyl, and then we'll add, you can add lithium aluminum hydride. And actually, it's worth writing out the mechanism for this because it's something that's like totally overlooked, but it's important for doing a lot of problems. So you could treat this lithium aluminum hydride as if it is just an H minus. Okay. And H minus is really strong. Like it's really good at what it's just really good as a nucleophile. And up here, this is negative and this is positive. So this H minus is going to come in and attack at the carbon, right? It's going to kick these electrons up. So there's that hydrogen down at the bottom, and now there's an O minus, right? And well, from there, second step, we have to add water. We have to do an aqueous workup, okay? And it's going to pull the hydrogen off of that water, right? This mechanism isn't super profound, right? You might not think like this is life-changing. The reason that I write it out is because every once in a while you'll see a problem that looks something like this, where they will let's actually make it a little bit more advanced and say we have a carboxylic acid now. Okay, and we give it a whole bunch of lithium aluminum hydride. Okay, so well, no, let me actually give you a problem, because I actually I prepared a problem for this. So how about we make this interesting, and we'll have one of these, which is called a lactone. Okay. And now we will give it lithium aluminum deuteride, so D4, which will react exactly the same, but that D is labeled. So we got to actually keep track of it. We're going to have to label it and say where it winds up. Okay. And okay, we'll say that there's an aqueous workup, but with D3O now. So the question is, what does it make? Well, it's not an H. I keep writing H's, but it's a D. So this D minus is going to come in, is going to attack the carbonyl, right? The electrons are going to kick up, but this O minus is a pretty good leaving group. So the electrons are just going to come back down and kick off that O minus. Okay. So we will get this structure here, which this is an aldehyde that we got back out at the end. So it's going to react again. Okay. And so now we're going to get an alcohol instead with 2 deuteriums and an O minus over here. Okay. These are deuteriums. Okay. And now we can protonate. So we can either protonate using H3O plus or D3O plus, right? I wrote over here D3O plus, so we would have deuteriums on both of these oxygens. If we used H3O plus, then we would get hydrogens on both of those oxygens. Either way, there's 2 deuteriums here. Okay. So this is a yeah, this is a case where the kind of mechanism here matters, and it's one that you should think about. Okay. Other cool stuff, yeah. So I mentioned there's this lithium aluminum hydride. So this can reduce everything. Okay, so that's worth keeping in mind. So in particular, it can reduce an alkyl halide, meaning it basically acts like SN2. Okay, which is really weird, and that's kind of something that's often overlooked. But if you see a deuterium that's attached onto a carbon with specific stereochemistry, it's very possible that it was through this. Okay, so it reduces those, and then it also reduces so it reduces acids, and then it also reduces everything else, right? And then sodium borohydride. Well, this one reduces ketones and it reduces aldehydes. Okay. So they have different strengths. Lithium aluminum hydride is way more powerful.
So if we're trying to reduce something, should we just automatically go to lithium LH4?
No.
Okay.
Unfortunately. The reason is because sodium borohydride is more selective. So you can have multiple functional groups. I mean, let's just say, for example, and I'm going to go way down here, right? If we want to reduce something like this, lithium aluminum hydride would just blast the whole thing, right, to be alcohols. in fact, writing it out because it's good practice. So, well, first let's count carbons because these are always hard to remember. So 1, 2, 3, 4, good, right? It'll turn both sides into an alcohol. And then sodium borohydride, well, it's a bit gentler, so it's not going to be able to reduce that acid. And I think you see the point, right? It makes one side an alcohol and the other side an acid. So, not always, no. Yeah.
Wait, so do we not want like both sides to turn into alcohol?
Well, it depends on what you want as your product. Yeah, it can totally vary based on what you're trying to achieve.
Okay, thank you.
Yeah. So you'll see this again actually in like next week or the week after, because when you do oxidations instead, there are things that can oxidize an alcohol to an aldehyde, and then there are things that can oxidize an alcohol to an aldehyde to an acid. Like some things will go and oxidize it all the way, and then some things will only oxidize it just a little bit. So, well, it's another situation where like you got to think about how oxidized you're trying to go. In this case, you're thinking about how reduced you want to go. But there's not as much subtlety as in this one as there is in the oxidations section. So, yeah, but you'll get to see those, and we're more worried about what's happening this week anyway. So, yeah. Okay. Good. And okay. So here, this is carbonyl additions, right? And then now we get to, oh, geez, this is the worst spelling ever. Okay. Organometallics. Okay, and this is like, now this is kind of like serious, right? Now we can do stuff with organometallics. Okay, and for the most part, although this is not entirely the case, for the most part, we react onto these carbonyls. Okay. You can also, with cuprates, you can use cuprates similar to SN2 substrates, reactants, although technically they have a different mechanism, but they give you the same product anyway. And you can also use cuprates to do epoxide openings, which you shouldn't do with Grignards or lithium reagents.
I had a question about cuprates. So like when we're doing a cuprate and halide reaction, can we attach just any R group to a cuprate, or does it have to just be a vinyl?
Oh no, it can be a different one. There's no reason it has to be vinyl or or like with a double bond.
So I can attach a phenyl group and just attack something with it.
Yeah, you totally can. Yeah, cuprates are a little bit broken. They're one of the things in like, so for example, you could take this and I don't know, whatever you like to pick, right? I don't know. Let's just pick something easy, right? And let's just go with like this, right? No reason you can't just swap it out. Okay. Cuprates are really, really powerful. They're super like good for doing a lot of different types of reactions. You'll encounter something along these lines again in organic chemistry too, which will come up eventually, right? There are a couple of these other types of reactions called coupling reactions, which basically let you just say like, okay, it doesn't matter what's on the other side. If there's like a bromine, well, I could just replace it with whatever I want, which is like crazy. And it lets you do some really broken chemistry because you could do like a bunch of things that would take a lot of reactions in like 1 or 2 steps. Yeah. And so the class doesn't usually focus on those things because like you know, you could use it to do some really powerful stuff, and they want you to actually learn like all of the reactions, right? So you don't just like say like, oh yeah, I can do everything with using cuprates. Yeah, that's not to say that you can totally do everything with cuprates, right? The other reactions that you know will be useful. You'll need to keep using those. So yeah, but these are really powerful, and there's a lot you could do with them. So these are important to know. Yeah, so you could use like a phenyl group. It doesn't even have to be a double bonded thing, right? Like, I mean, whoops, that is a double bonded thing. Like, I don't know. You could do like this is totally an okay cuprate. Let me use. Oh no. Oh geez. Okay, I thought I almost got rid of the whole thing. Okay. Okay. Right. And so you could do MGBR too. Actually, let's go really wild and pick something that's just super weird. Magnesium chloride there. Okay. Right. Because it doesn't have to be a bromine to make a Grignard reagent. It's just usually a bromine. So no reason you can't use this. Okay.
So like any hydrocarbon that you can put there?
Yeah. So I guess there are exceptions, right? Which is okay. This is not a valid hydrocarbon. Right.
Well, it's oxygen, right?
Yeah,
Or is
yeah,
that
exactly.
not why?
Right. So like it would just attack itself, which is like strange. So carbonyls aren't allowed. Okay. So that's no good. Alcohols are not allowed because remember that this is like these are super basic, so it would just deprotonate and you'd lose your whole reactant. So also no bueno. Another thing which is never really explained why for a very long time. It's one of those things where I hate to say it, but it shows up like at the end of World War II. You can't use nitriles. Okay. Right. And at the risk of, confusing you or giving you more that you need to know, it's because these nitriles, right? This part is plus, this part is minus. So if you have like a C minus, it'll just come in and attack it, just like a carbonyl. Right.
Wait, so can hydrocarbons have things other than hydrogen and carbon?
Oh, you said no, they can't.
Oh, okay.
Yeah,
I was confused now.
hydrocarbon. Yeah, I was just thinking in general. In general, there are some things that you can't have on these things, but hydrocarbons, just carbons and hydrogens, should be totally okay. So, good.
I'm just a little confused, like why these are so useful. Like, when should I think to use them in a synthesis or anything like that? Like, I just don't get the point of them, I guess.
Do you mean cuprates specifically or organometallics as a whole?
I think cuprates more so.
Yeah. So here, let me just do this. Okay. So yeah, the thing with cuprates is they're weaker than other organometallics, right? So like, other, I don't know what else, right? Like, let's just go really simple, right? CH3 lithium, right? This thing can attack most carbonyl things, right? So for example, if we have like an ester, well, this is going to have no problem, right? Like no problem at all. In fact, it'll kick the ester off and then it'll go in for a second round, right? And then you'll get this alcohol. I should write O minus, right? So lithiums, and the same for Grignards, they'll just keep going. They'll attack like all the things. They won't attack carboxylic acids usually. Those are too bad in terms of reactivity. But things like esters, these will have no problem, right? And then you go to one of these, a cuprate, right? And you give it an ester, and nothing. No reaction. They're not strong enough. They're not actually good enough, right? So like, what the hell's the point of them if they're just gonna be worse than this? So there's a point to them, which is that they won't add to ketones in general. Okay, so you can even give it a ketone. Right? Nothing. Okay. So the reason that these are useful in the first place is because you can give them, and they won't make tertiary alcohols. They will stop at a ketone. They won't stop at an aldehyde, but what can you do? Right? Yeah, so for example, you can imagine giving this like an acid chloride, and there you go, right? That comes out perfectly nice. Whereas if you give what we were working with earlier, CH3 lithium, if we give this an acid chloride, well, it's going to go on, and it's going to make this O-, this tertiary alcohol. Okay. Sometimes we don't want that. So that's the nice part about cuprates. The fact that they work this way is also nice because you get to be a little bit selective with them. So, well, why don't I actually start writing out a tape, like or just writing out a list, because there's some reasons why cuprates are nice. So the cuprates are nice because they can stop at ketones. Or they don't make tertiary alcohols.
Wait, before you keep going, did you say that lithium kicks off esters?
Yes. Yeah.
Could you say briefly how it does that? Just because, like, on one of the problem sets, like something did kick off ester, and I was really confused about that.
Yeah. Where did I write it? I wrote it over here. Yeah. So what happens is that this is like a CH3 minus, right? So it'll come up here. It'll attack the carbonyl, right? And then actually, let me do this in a different color. Let's pick blue this time. Right. So it'll come up here and it'll attack the carbonyl, right? So this will give us this O- with that methyl hanging off. Sorry. Right? And this rest of the ester that was there. And what happens is, well, if we were to kick these electrons, well, push these electrons back down, right? And then give that bond to that oxygen, well, we'll be left with this plus this O-. And this is normally not really a great leaving group. Like it's not that great, right? If we think about this O-, it's got a peak, like an OH on like methanol has a pK of like 16. So it doesn't normally like being deprotonated. It takes some kind of serious work to get it deprotonated. But
and
this took
is the lithium capable? Why is the lithium capable of that, but the sodium borohydride isn't?
So I guess it comes down to the fact that like sodium borohydride is a milder reagent. Um, it's weaker. It's like not as strong of one. Lithium aluminum hydride is a really strong one, but sodium borohydride isn't, and it just kind of stops before being able to cleave esters like this. Yeah, I'm not sure if I can give a much more satisfying answer than that, because like it probably comes down to like electronegativity of, let's say, the boron versus of aluminum or something in the lithium aluminum hydride. Um, yeah, like, well, I guess part of it is the fact that like sodium borohydride is fairly mild, but to make this CH3 lithium, well, you take like CH3Br, for example, right? And then you have to give it lithium metal. And you know what lithium metal does? If you just have a block of it lying around, it blows up, right? So you have to put some serious work into making this organolithium in the first place. So there's a lot of like energy, like a lot of power stored in there, whereas sodium borohydride doesn't really have that.
Gotcha. Thank you.
Okay, yeah, that's at least the way that I like to think about it. The harder something is to make, the stronger it is, usually. And well, starting with like lithium metal or sodium metal or something, that's about as strong as you can get. At least, yeah. At least that's the way I like to think about it. It's a little bit of one of those like not super accurate and not super like faithful ways of thinking about these things, but well, works perfectly fine. So yeah, you will get as far as you need to by doing that. Yeah, so the idea is here we have these cuprates, and well, they're nice because they can stop at ketones, right? And they're also nice because you could do reactions like this, where, let me even be more specific, right? You could do something that looks, let me be even more specific. You could do something that looks like this. You can have like a bromine, or you know, yeah, let's just stick with bromine because it's a good leaving group, right? Or you could have, you might be able to have like an O-tosyl group, for example, or some other good leaving group, but I think it might specifically be bromine, or another halogen that you want to go with. Anyway, yeah, you could take one of these like halogens or a good leaving group, and well, give it, I don't know, whatever you like. Let's just keep it simple and stick with that, right? And it'll just swap on. I drew an extra carbon there, but it will just replace itself. It'll invert stereochemistry too, almost like SN2. The mechanism is different. It's not the SN2 mechanism. But if all we care about is the product, well, it works, right? It gives you inversion of stereochemistry. It is stereospecific. Like, that's a nice reaction that you can't do. You definitely can't do this with Grignards or organolithiums. Okay. And well, there are also some extra reactions where you could just swap these things. I actually, before I even get into that, I should say, they're also nice because they work on epoxides, which, well, Grignards and lithiums won't. Whoops. Oh no. Sorry about that. Yeah, so Grignards and lithiums won't. They're too powerful. They will just totally react on them, right? Like you can use Grignards and lithiums on this, for example, right? Like this is lithium, I don't know, CH3, right? Like this is okay. This is totally fine. All right, whatever. You can do this. O-, and then you get one of these. right? But to do something like this, now you want it to be specific to one of the two sides. Well, now you need to actually use a cuprate. And I'm going to keep using the same one because it's, well, not that interesting, right? And it'll react as if it's like an SN2 thing. Okay. So it attacked the less substituted carbon. Okay. Yeah. Yeah, let me think what else there is remaining. So I think, yeah, I think that covers it. Yeah, and then you could also do these coupling reactions, which I think were briefly mentioned. So if you have like this R2ClI, right? And for example, a bromine on a double bond, well, you could just replace that bromine with one of these. Okay. Which is kind of crazy, but you can do it. So yeah, that's an option. Okay. And then I guess the like kind of last thing for me to say about all of this stuff is that let me zoom in. Okay, there we go. Yeah, the last thing to kind of say about this is that there's different reactivity. So I kind of already alluded to this and used it, like I kind of assumed it already, but there are different reactivities to each of these things. So most reactive is acid chlorides and these guys. Anybody remember what these are called? Any chance?
Acid anhydrides.
Yeah, so these are acid anhydrides. You might often see them just called anhydrides, but acid anhydrides. Okay, so these are more reactive. Should put. So in terms of reactivity, these are more reactive than what? Anybody?
Formaldehyde.
Yeah.
And aldehydes.
Formaldehyde. Yeah, we hardly ever, we don't use that formaldehyde that often to do this sort of stuff. At least in the context of this class, I haven't seen it show up very much. So aldehydes. Maybe let me just draw it like I'm a normal person. Here we go. So aldehydes. Okay. And what's worse than an aldehyde?
Ketones.
Yeah, right. So ketones. And then, well, keep working our way down. There's not that much to go. So how about I just write? So we got esters. And lastly
Amides.
is amides. Exactly. Right. So esters and then amides, right? Large part being that, well, for an ester, for example, you can get this resonance, which will kind of mess up the whole like charge that you had here, right? Like you had a whole nice thing going, right? And then you put this resonance thing on there and it kind of messes that up. So that's not great.
Adam, I have a question. Where do carboxylic acids fall on this?
Way at the bottom.
So generally, do we have to worry about them if we see them in a reaction?
No. Not for Grignard's or lithium reagents. So it's possible, and they love doing stuff like this, that they would give you a reaction which looks like this, right? The idea being that you would say like, oh, this is an organometallic, here's a carbonyl, right? So I'm just going to replace that. So I'm just going to like add this ethyl group onto the carbonyl. But that's no good because, well, this is an acid, right? This hydrogen will come off really easily, and this thing is super basic. You have to put a ton of work into getting this thing. So, well, it's pretty lame, but yeah. This is the sort of thing that like shows up every once in a while. It's like, I got you, but yeah. I don't think, yeah, no, well, no, I know that you can't do any of these reactions on alcohols. There is, well, eventually you'll be able to do stuff like this, but the way that you do it in practice is if you have an alcohol and you want to do a reaction on here, what you do is there's a special reagent that you can use, and it just takes it back up all the way up to the top of the series, the reactivity series. And from there, well, it's easy. So that'll come in time, but for now, well, for now we'll just keep it as is. You can't do that. So okay, cool. Yeah, there's one other note, I guess. I said this was the last thing, but it's not. There's one other note, which is that I know in the lectures he mentioned this thing called a Weinreb amide. And I know in the past I've been like, yeah, it's like a really specific thing, like they're not going to ask about it, right? And then they asked this huge exam question about it, which was like really specific. So I guess it is worth knowing, and you really can't get away with not like worrying about something. Anyway, the point is that the Weinreb amide, it has like a structure that looks like this. So it has this oxygen on the amide. And the idea is that when you add, I don't know, like, I'm just going to call it R minus because whatever, that's good enough. So the idea is that when you add, like, in the lecture it was used a Grignard, right? So when you add one of these things, well, it's not even a plus. It's just this. When you add one of these, it stabilizes this thing. Okay. And the idea is that this won't, like, the amide won't come off. It's gonna stay on there. So then you just do an aqueous workup. This NO is going to this oh, I should have added this R down here. This whole thing will come off with H3O plus. Well, the way I'm drawing it is a little bit messy, but the idea is that you just wind up with the ketone instead. Normally, if you use the Grignard, it would go all the way, it would make a tertiary alcohol. But because this thing's stable, this Weinreb amide stabilizes that O minus, well, you don't. And so you just get a ketone out at the end. That's not that exciting anyway. We could do that with cuprates, right? If you have an acid chloride or like an acid bromide or whatever, right? This is like, we live in the future, and we've got better stuff than this. So no reason you can't just do this. No, it's totally fine. yeah, I'm sure that wine-rab amides have their place and their use. And there are questions that they could ask you that like would necessitate the use of a wine-rab amide. But if you're doing like a synthesis, are you kidding? No, don't bother. It's not worth your effort. Cuprates are easy to make, and if you could just use an acid chloride or an anhydride, well, do it. Okay. Okay, so that is plenty of review for now. Let's actually work on some problems. Okay. Cool. Here we go. So let's start with one of these roadmaps, which are long and whoops. Here we go. So let's, oh no. Okay. So let's start with one of these. And well, the question is, okay, we have to fill in the rest of everything that's in this huge map. These things are complicated, right? And okay, yes, they're not going to ask you a roadmap on your exam, but like, well, they're going to ask you all these individual reactions on your exam anyway. So yeah, it'll be good practice anyway, right? Okay. So, okay, how about we, because like, you're gonna have to do these things out on your quiz. So how about you take like a minute or two and start working through this? Like actually working through it, because I'm not gonna be there to take your quiz for you, right? So yeah, give it a minute or two of some thought. I'll keep it up here. Oh no. Oh, I zoomed in too. All right, never mind. I'll keep it like this. Think about it. It's been like 2 or 3 minutes. I think. I wasn't really keeping time. Okay. So, well, why don't we think about one of the pathways at least, right? So why don't we start with A, B, C? Sure, right? It's in alphabetical order, easy. So, well, what do you think for A, right? Hopefully all of you went through this pathway because, well, you needed to do pretty much the rest of the problem. So what's going to happen in this first reaction?
Is it just a deprotonation?
Yeah, that's all that's going to happen.
I was
Right.
just confused about why the BRMG is written there. Like, I thought counter ions didn't really matter.
Yeah, they don't really matter. In this case, they wrote it in, but, well, I guess it's just because, like, otherwise they would have to write like a minus charge, and that's kind of like ugly. And really, it does like have a counter ion. We just often leave it out because it's not that interesting, but it exists. Yeah. So anyway, that's all I'll say. You're right. You're totally right, and it's just a deprotonation, right? And again, they'll throw this at you. Well, I don't know if they will, but they totally can. But there is just a deprotonation, right? And so it'll pull this hydrogen off. What's the pKa of this hydrogen?
$25.
Yeah, there we go. Yeah, that's a number that should always be in the back of your mind, right? Whenever you see an alkyne, if the number 25 doesn't come to mind, well, get there. It's not that important, but, well, it's just a common question. At least I like to ask it. Okay, and how about we go through B and C, right? So, well, now we have this acetylide, right? Or triple bond minus with extra stuff. I don't know, whatever you want to call it, right? And we're giving this epoxide. So is this an acidic or a basic epoxide opening? And maybe to make the question more interesting, is it acidic or basic? And does that mean it'll attack on the more or less substituted side?
It'll occur at the less substituted side.
Yeah. Yeah, and so this is a basic epoxide opening, right? I mean, this thing here is really basic. It'll pull hydrogens off whatever it has to. But if you don't give it any, then, well, it'll do an epoxide opening and it'll attack the less substituted side. Okay. Which is to say we wind up getting, well, we'll wind up getting something that looks like this, right? And then get rid of that bond, and there's a minus there. And then we do a workup to get that alcohol. So, well, why don't I write it out? So we add this guy, it'll attack on the less substituted side. And what that means is, oops. Oh, I totally drew it on the wrong side above. Sorry. There we go. Okay. It attaches to the right side. Okay, and then, well, there's a workup, but that's not that interesting. So this was A, and now we get B. Looks like that. Okay, and, well, if anybody wants, you can check this formula, and I think it should wind up being okay, right? You're all taking Orgo Lab, right? And well, some people might not be. Yeah, I forgot about that. But those of you who are, we learned about in NMR. I say this because I'm also currently taking Orgo Lab, which is a little bit wrong if you think about it, but it's okay. Anyway, when we talked about NMR in that class, there's this idea about degrees of unsaturation. So if you want, you can calculate this as 2 degrees of unsaturation. Oh, there's 2 multiple bonds, or there's a triple bond that corresponds. Okay, that's an easy way to check, but well, you don't need to do that. You could just count this molecule, and that's totally fine too. It could just be nice to bring things together every once in a while. Anyway, the point is, we've got this this alcohol with the triple bond, and then we add sulfuric. It's a bit hard to read because it's sideways, but we add sulfuric acid, and then we heat it. And so what does that sound like?
Dehydration.
Yeah, exactly. Or E1, we might write, but dehydration is perfectly fine too. Okay, and well, are we going to make the trans or the cis alkene? I guess here it shows it being the trans alkene, but we'll kind of make both, right? Like, this will make the trans alkene slightly more because it's a little bit more favorable. Whatever. Let's just say we make the trans alkene, make our lives a bit nicer, right? Okay, and let's keep track of our carbons. So this goes here. Okay. Nice. And what is this up here?
Lindlar's catalyst.
Yeah. Okay, and again, remember, this is one of those situations where they don't really expect that, like, you don't need to know all the reagents. You can write Lindlar's catalyst and you'll get full credit for it, unless they've specified otherwise. But in the past, that's always been totally okay. So, yeah, if you want, you can remember. Well, I guess I should actually say, this is Lindlar's catalyst. The H2 doesn't count. It's not part of it. So this is H2 and Lindlar. Okay.
So I don't like for part C where we made the trans alkene. Is it because trans alkenes are more stable than cis alkenes, or is there like another reason?
Yeah, they are a bit more stable. Yeah, I guess you would prefer the trans alkene because it is a bit more stable. Like I think in reality the actual like stability of the trans versus the cis alkene is like super minor. But we did know that this final product here, that's the trans alkene. So, well, we can fill in the intermediate. Yeah. Anyway, so this was C over here. Cool. Let's go back up. And, well, if you were still working on the problem, maybe you've had a chance to finish this up. But, well, either way. Here we go. So we have over here, so we're taking A, which has a minus charge, and then we're adding deuterium oxide, D2O, right? And the structure is C4H5D, right? And so what reaction are we going to do? This one's not really mind-blowing.
Oxymercurization. That one. Oxymercuration. Demercuration, right?
In
Because
with
it's
D2O?
Hg.
Wait.
Maybe not. I don't know.
Where am I? Oh.
I think it's something HGSO4 and thought that, but maybe not.
Oh, I don't. You might have been thinking. So here in the next step, there's a D2SO4. That might be it. Yeah, I don't know. I haven't looked ahead. But in this case, we're just adding D2O. So, well, it's just water, right? It's just like normal water. It reacts the same at least. And this thing is really basic, so it's just gonna pull a hydrogen off of there. Except it's not gonna pull just a hydrogen, it's gonna pull a deuterium, right? To a D. That's it. You can check the structure, you can count the carbons. Hopefully they're all there, but well, I lose them every once in a while. So, oh yeah, the next one does have HgSO4. I didn't even see it was on the bottom. So you're totally right there. Yeah, and so what do we do with this? Okay, what do we do now with HgSO4? Oh, it's D. Yeah, okay. There's deuteriums. Anyway, what do we do with it?
It makes a methyl ketone.
Yeah, exactly. It does. So that is good. Okay, so here we had a triple bond, and well, we're adding deuteriums here, so this gets more complicated. Okay. But well, we started here, and all we've done is add this oxygen, which, well, that's fine, right? It's oxygen, it's just a normal oxygen. And then we've added a bunch of deuteriums too. Okay. So wherever we've added new hydrogens, we could say those are deuteriums instead. In other words, well, this already has its 4 bonds, so we don't need to worry about it, right? This had a deuterium that's old. And well, here's this guy and these, right? The only other place that we've added hydrogens is at the end here, because this needs 2 more hydrogens. So that looks good.
Wait, are the hydrogens from the deuterium and the HgSO4, or are they from the D2O?
They're from the D2O, okay. or the D2SO4. I think one or two of them come from. I think one comes from the sulfuric acid and the other one comes from the D2O. Don't quote me on that. If you had, for example, H2SO4 and D2O, you can't really say what would happen, because like hydrogens swap off really easily, right? Yeah. So sometimes it would be hydrogen, sometimes it would be deuterium. You'd get like a whole mixture, and it would be, you can't really say for sure.
Okay.
Yeah. But anyway, it is yeah, you can't like use hydrogens and deuteriums at the same time, but yeah, this works.
Would this molecule, sorry to interrupt, would it be subject to tautomerization between like maybe having an enol if you had the double bond between the carbon and the other carbon with the deuteriums on it?
Yeah, exactly. So this actually does go through a keto-enol tautomerization, and so first it goes to this structure, and then it does keto-enol tautomerization to get to the final structure. Okay, it's an acidic keto-enol tautomerization, right? Which differs from a basic one. They have different mechanisms, so those are good to know. I would highly recommend looking those over, right? Yeah, so it does go through a keto-enol tautomerization.
So that just like was the double bond, right?
Huh?
The tautomerization thing. Like,
Yeah,
like the effect of it is really just moving the double bond up and getting rid of the deuterium.
Yeah, you could think about it that way. Yeah, it's totally fine. Yeah. Cool. Okay. And let's say we didn't go that way, and instead we went sodium amide, and then we added this aldehyde, and then we did a workup. Okay, so what is the sodium amide going to do?
Take the deuterium off.
Okay. So then what does it do
sorry.
to the aldehyde? What?
Wouldn't it be negatively charged?
Yeah. And so then what happens?
Oh,
with
with the
aldehyde?
sorry. Then it would take it. It would go to the double bond on the aldehyde. Like
Yeah.
where the
So,
carbonyl is.
yeah, exactly. So this whole thing will attack onto that carbonyl, right? In other words, our structure will be this, right? Well, there's a hydrogen here. That's not that interesting, although we don't want to forget it. And then we've added this acetylide, right? And well, they say that we do a workup, so let's be sure to fill in the rest and add that hydrogen. Okay. The structure here, it said, was C7H12O. And well, I'm not going to do it, but you're welcome to count out all the carbons and hydrogens and see that that's what it is. Okay. Cool. And well, the last part that they say is that you can use concentrated sulfuric acid and heat followed by H2 and Lindlar's catalyst, and you wind up getting the same thing out as we got earlier. Okay, it's kind of nice if we go back up here, see like, oh look, it goes this way and then it goes back around. Anyway, whatever. It's two ways of making the same thing. Okay, cool, but we missed this whole side here, so how about we just finish that one off, right? Okay, here's this side, right? One, we add diisocyanylborane. The other one, okay, well, yeah, we finish off the reaction. So this is your hydroboration. What kind of product do we get out at the end?
An aldehyde.
Yeah, exactly. Right. Also through keto-enol tautomerization. So also a good thing to know. Right? Okay. And then last thing is that we use this guy, this one, which is actually called acetylide, and then do a workup afterwards, right? And well, I'll save you the unmute click, and we just did one of those earlier. We added an acetylide to an aldehyde, right? So, well, let's just do that again. We did a workup, so we wind up getting an alcohol at the end, and there we go. Right. Okay. Oh, that's not a plus. Oops, whatever. Sorry. There we go. And this was structure H. Nice. Okay. We have next. Okay. Yeah. Anyway, I'm sure people will trickle out at some point. I have one of those like forms, just like a sign-in form, so fill that out at some point. I'll send it in the chat. You don't have to do it now, just fill it out at some point. Helps me count, just know how many people came. They make me collect pen IDs for whatever reason to do that, but well, that's all it is. It's just helpful to know how many people were here. But you can fill it out later. I'll send the link again anyway. Yeah, every once in a while, whatever. Okay, so how about we get another one? And now the question is, and I have to scroll way back up to get this. The question is, what are the reagents that you need to do this reaction? So, well, why don't I even put like 3 of these up? I'll put 2 more up. And again, I mean, you're gonna have to do these on your own tomorrow, right? So there's no sense in me just telling you what the answers are. So I'll put these up and I'll give you a minute to think about it, or like 2 minutes, right? And then we'll go through them. So let's put 90 seconds on the clock. Seems like a good number. I should mention they are multi-step, so you should write like 3 steps for each. Okay, my timer went off, so that says it was 90 seconds. Okay, yeah, so here we go. Here's the first one. What are we gonna do? Well, and I say this pretty often at this point, but I really do believe it's true at this point in the class. It's not gonna it's really not gonna be obvious how you get from point A to point B, right? Like this is totally not something that you can do in 1 step. It'll be a bit more complicated. I told you it could be done in 3 steps, but yeah. So anyway, the way that is like really powerful and good to do this is to go backwards. So we'll use retrosynthesis. Okay. And well, how can we make this final structure?
Can that just be from like a free radical bromination?
Yeah, exactly. Right. So this is an allylic bromide, right? And so allylic bromination is something that we can totally do, right? And what do we need to use to do it?
NBS.
Yeah, right. Maybe that's a bit of a silly question for me to ask you guys because, well, by this point, this is some real old stuff. Okay, right. So use NBS and light. You can also use heat, but that's a technicality that you don't need to worry about. Cool, right? And now we want this double bond. And okay, how would we have gotten that double bond? What's like one of the better ways that we know how to get double bonds? That might work.
Elimination.
Okay, so what do you want to eliminate?
So we could have substituted a bromine at some point, which we can use to eliminate, or like protonate a hydroxy group and make it leave.
Yeah. So okay, well, so there's two options here, right? So we could either have had an OH, right, and then heated it in sulfuric acid, and then that'll give us that double bond. And well, I guess just to finish that one off, how do we get to that OH from the starting compound?
Can you just reduce it with like hydrogen over platinum?
So I actually think you might be able to, but in this case, that's a bit dangerous. So if you remember that that's the case, then like totally and go ahead. I know whenever I've dealt with carbonyls, it's always just been like use a reducing agent. So in my, well, what I would do is use one of the two reducing agents. So lithium aluminum hydride or sodium borohydride, either one. But it might be the case, and I can't remember exactly, but there are ways to use hydrogen and some catalyst. I think there's, yeah, I can't remember exactly. But if that is the case, and you do remember specifically, then yeah, go for it. But, well, I like to be on the safe side, and so you could always go overkill with lithium aluminum hydride. Okay. Anyway, the other way that you suggested was with a bromine on there, right? But this will take an extra step or two. So this will be a little bit more work. In fact, it might take an extra 3 steps or so. With this carbonyl, you'll probably have to, well, we're not making any carbon-carbon bonds, so there's not a lot else that we can do with carbonyls besides reduce them. So we're going to reduce them. And getting this bromine on will be a little bit more tough because we'll probably have to make a double bond, and then we'll have to brominate from there. But once we're already here, then we're one step away from the end. The bromine probably is going to be a little bit more work than it's worth. So we'll skip it.
Wait, for the bromine, you said you're going to make a double bond and then put bromine on and then take the bromine back off?
Oh. That's a bit silly, right? Yeah.
Yeah.
Yeah. So okay, in that case, yeah. So this is the way to do it. I see what you mean. Yeah. So we'll stick with this, right? I guess there isn't really any better way to do it. Cool. What's next? Okay, we have a ring. We're starting with this ring, and then oh man, we go to this absolute mess. Okay.
So I had a question on A.
Yeah.
For the lithium aluminum H4 there, do you not need a solvent or anything to protonate the oxygen afterwards? Is that included in there?
You are right. Yeah, we should protonate.
Okay, thank you.
But, well, and anyway, you're right. You're totally right. And that's like something that I just missed. And thank you for catching me on it. But very minor note, the next step is acid. So we could have skipped it. But in that case, we should have written this as an O-. Anyway, that's like that's like an oh we got lucky sort of situation. You're totally right. You should do aqueous workups. You definitely should. Yes.
Awesome. Thank you.
Yeah. Okay. Yeah. Thanks for agreeing with that. That was. Thank you. Whenever you guys catch me on my errors, thank you, because as you could tell, they show up a lot. So. Yeah. Okay. Here we go. This is going to be a real pain to make, right? But well, we know at least one good thing, and let me even go and pull this up on a new, on a nice blank canvas, so that I've got plenty of room. But so this will be a pain. But here's the nice thing, which is that. Here we go. Okay. So the nice thing is we can at least see that here we started with a ring and well, now it's open, or at least there is no ring anymore at the end. So presumably it'll be opened at some point. Okay. How have we learned? And I think there's like really only one way that we've learned. How have we learned to break carbon-carbon bonds? Because we don't talk about that one as often.
If you have an alkene and you use ozone, it'll create like the double bond to an oxygen at the end and open the ring.
Could you also do the hot potassium permanganate?
Yes. And in fact, if you can like foresee what will happen, they'll actually work exactly the same. So in this case, you could really use either. Yeah, ozonolysis is gentler though, and well, it's like a nicer thing to do in the lab. So we'll go with ozone, but we'll point out where that happens anyway. The thing is, this has alcohols on at the ends on these two sides, so that wouldn't have worked, right? So when we do ozonolysis or hot potassium permanganate, what do we get out instead of alcohols?
Carbonyls.
Yeah, exactly. Right. Oh, yeah, I drew that wrong. Yeah, you're exactly right. So we get carbonyls out instead. Okay. Well, how would we have gone from these carbonyls up to these alcohols? Well, okay. We just talked about it in the last problem, right? So, oh, someone was going to unmute and say it, but you pick your reducing agent of choice, right? So lithium aluminum hydride, right? In this case, no reason not to use it. Okay. So it's fine.
And then you need like H3O plus to put the hydrogens on.
Yes, thank you. Yeah. I guess it's a really easy thing to overlook. At least for me, it totally is. So don't overlook the aqueous workup because it is important and it does matter. So keep that in mind. Okay. Anyway, now we're here, right? And well, you might be able to see now where this came from, right? And if I want to draw this a bit more suggestively, then we could count carbons because this is like a real area to screw up, right? So there's 6 carbons here, so that means this had to have come from a 6-carbon ring, right? And well, oh, I want a different color. There we go. And well, if I want to draw this like way nicer, I'm going to keep this side to be exactly the same, and then we go down to 5 up to 4, except now we're going to change how we draw it. So 3 is up here, 2, 1, and then draw that carbonyl down there, and then the phenyl group up here. Okay. And now, I don't know, however you want to think about ozonolysis is what you should follow, but I like to think about it as taking a structure like this with a double bond. Okay, and then just splitting it and replacing each side with an oxygen. So that's how I like to think about it, but you do you. Okay, and you know, we could have done this by 1 ozone, 2 dimethyl sulfide, SME2, as I like to think about it, right? It's another good option, okay? Or, well, alternatively, you could just blast the shit out of it, right? There you go. Great. Well, now there is a problem. No? This is hard. This is a really hard thing to do. In fact, like, I can't think of any way to do this. If you can, speak now, but I don't know. That's hard. We screwed up. Okay, we did. So, well, I have to rethink it. So maybe we jumped the gun here, right? It's totally possible that we did. And, well, we have to get these phenyl groups on there, right? So we have to have made those carbon-carbon bonds, and we just learned how to make carbon-carbon bonds. So why don't I get rid of this stuff, because we know it's not going to work. In fact, I'll get rid of these guys too. Okay, this is not it. It's not gonna do the job. Okay. Maybe making these alcohols by reduction isn't gonna be it either, right? So instead, if we know that we're gonna do ozonolysis at some point, why don't we add the phenols on later? Okay, so we'll skip that, and instead we'll go on this end, right? So we want to do ozonolysis, so we want a double bond, right? And, well, this is old news. So we use concentrated sulfuric acid and heat, right? And then we could repeat what we just said, and we do ozonolysis. Yeah. And in this case, we could do, now it'll matter whether we do a reductive or oxidative workup. Let's do a reductive one. Let's say that we do it, right? And, well, similar to what we had, we get this. Okay. Now let me get rid of all this extra stuff here, and what can we do at this point? Now we're almost there. In fact, I'll just draw a single arrow and say we can do it in one step. So what can we do now? How can we make these alcohols and add the phenols?
Can we use a phenyl cuprate?
Sure, that's a good choice. Right. So pH 2. I don't even need to write this stuff, right? I'm really used to that, but here we go, right? And just to give it a little bit of life, a little bit of, I don't know, diversity, right? We'll use magnesium cuprate, magnesium chloride. Why not? Make things more interesting, right? And, well, this time I'm not going to forget we need an aqueous workup. So there we go. Okay. And that'll get you both phenyl groups on there. That'll get you the alcohols. In fact, it'll do both of those in like one step. It's kind of nice. So that's a good choice. Okay. No, not what I wanted. Okay. All right, cool. And how about the next one? Let's keep going. We're pushing on 9 o'clock, I know, as we always are. This is like super standard. I have some extra problems too, so I don't know if you guys like are big fans of sticking around. I've got a couple extras. May or may not be fun. They won't be fun, but well, that actually, yeah.
Adam, for the last one, I thought cuprates couldn't react with aldehydes.
Is that so? So I thought they could, but I might be. You might be right on that. Yeah. How about we use a? It's not letting me erase. Oh no, we might be stuck with a cuprate. There we go.
I have it down in my notes that like cuprates can only react with acid chlorides, like out of the carbonyl ones.
Okay. Yeah, that might be the case. I might have misspoken. They can react with acid chlorides and anhydrides for sure. Yeah, I guess it could be the case that they don't react with aldehydes. In fact, I already have a thing up about what they can react with, so why don't I just check that because I already have it up. They can. Oh, I think it's loading. Okay. Well, I have a list, except it's like super blurry and it's just not loading for whatever reason. That's kind of okay. Yeah, I guess I would say that they don't. Oh, this thing doesn't say. Okay, yeah. If it said somewhere that they don't react with aldehydes, then follow that. In this case, we'll just use a Grignard reagent instead. Yeah.
If you use Grignards, would you have to worry about it adding 2 phenyl groups? Because it forms a ketone.
In this case, you wouldn't. The reason being is that this hydrogen is never coming off. So once you put one phenyl group on there, you'll get an O-, you'll get a hydrogen, and you'll get that phenyl group. And none of those 3 is gonna leave. So.
Okay, so is that only the case for like an aldehyde? Like if you just had a true ketone, it would do it twice or not?
A ketone, in this case, a ketone wouldn't either. So if we have like, this should just be one. Oh my God. Just one phenyl group. So this ketone wouldn't either. It would just add once and those carbon groups aren't going to come off. What will come off is an ester. So an ester will break open. Acid chlorides and anhydrides will also break open because those have leaving groups. But you're not going to pull off carbons or hydrogens off of these.
Okay. So that only happens when you have a good leaving group.
Yeah, exactly.
Okay, thank you.
Yeah. Yeah, you're right. So, yeah, sorry about that. Yeah, so, okay, don't use cuprates for aldehydes. Yeah, okay, I got that mixed up. Cool. Anyway, let's go down to here. Okay. And this is going to be ugly, right? Because we have this alcohol and we have a deuterium and there's syn, and so we're supposed to get the same stereochemistry. We're supposed to like care about stereochemistry. At least, I guess I should say regiochemistry, but whatever. Right. Okay. So what do we do? Well, there's this iodine here, and we're going to be adding 2 different things on here anyway, right? So what might be a reasonable thing to do about this iodine, or just with this molecule?
Me too.
Yeah, let's just take this thing off because this is not like it's just gonna get in the way, or it's good. It's it's good. It's just waiting to be taken off. So, we'll do that. Right. Pick your favorite. Well, this is the Zaitsev product. However you want to spell it. So pick your favorite small base. Right. Again, no need to be creative. Sodium hydroxide will work fine. Okay. So there you go. Now we're here, right? Oh, and all right, now we got to do some ugly stuff. But let's not think about this too hard, okay? Let's not, right? We want to add an alcohol, and we're adding it to the less substituted carbon of this double bond. How do you do that?
Don't we just want to do hydroboration?
Yeah, sure, right? Like, no reason we can't do it, right? And so let's use BH3.THF. Okay. And then, well, let's just do it one step at a time, right? So here's an H, and why don't I even just write this in? Oh, wait, and there's the BH2, right? And then step 2, we get rid of it, right? AOH, and then there's also some hydrogen peroxide that goes in here or whatever. Yeah, whatever, right? And that puts this alcohol on there. Okay. Yeah, but this deuterium isn't there. So at what step should I have added the deuterium, or should you have added the deuterium?
Is it in like the borane?
Yeah, exactly. So instead of BH3, nobody's saying we can't write BD3, right? Sure, why not? Yeah, so we can do that in there and put it, there we go. There's a D now, and okay, we do actually get the right final product. Okay, there we go. Didn't have to think too hard. Yeah, looking at this, focusing on this alcohol and thinking about what can put it there, that kind of got us there. Or got us most of the way, right? And then we had to go back and do a little thinking, but well, you always got to think a little bit, I guess. Okay. Cool. Okay. Let's see. We're coming up on 9 p.m., which is technically the time that this is supposed to end. Yeah, we've gone through like kind of the two like main problems on the worksheet. There are a couple extras, so I can put those up on the screen right now. They're on the Canvas site anyway, like the workshop Canvas site. If you're not on that, you can send me an email or type in your like email in the chat, and I can add you. Like you could DM me or whatever in the chat. Yeah. Anyway. Yeah, so here they are, right? You could, I don't know, take a screenshot or whatever, right? So here's one of them. Here's the other one, right? And this totally happened last time too, where we didn't like really finish all the problems, right? We kind of like got through most of them, and then I was like, oh, well, you can finish the rest. I have extra problems though, and then a bunch of people were like, yeah, I'd much rather do the extra problems, and so that's what we did. Is it like a safe bet to say that that's the same case, right? Because you can look at these problems again, like later, right? These problems aren't going anywhere; they're on the canvas. So should I write up some extra problems and then give you a minute to think about those? Yeah. All right. I saw a thumbs up and a nod. So 2 different signs of agreement. So that's double the yes. All right. Yeah, these are good problems too. You should totally do them. They're also good problems, and you should work on them, right? The answer key will be up though, so well you could check against the answer key too. All right, let's get to work. Here we go. how about I start writing a couple and you can have some fun. So here we go. Let's write. I gotta think what order to go to write these in. So how about we start with this, and then let's start with some good stuff right off the bat. Why don't I even give this a solvent and say THF? Because THF is extra irrelevant in this case. So what does that make? There's a question. Okay, cool. Okay, here's write out a mechanism. So how about you write out a mechanism for something that looks like this? Oh yeah, we got epoxide, so we're starting out really good, right? And just to throw you off, I'm going to give you a compound that you might not see that often, LDA, but well, you have seen it, so it's fair game. So there's LDA and there's this H3O plus, and the final structure that you make is this. Okay. So that's going to be fun for you. And then I'll save the monster for later. It's a really long one, really big one. Oh wait, let me keep that one on the screen so you can work on it. What's next? We'll stick on epoxides for a moment. There we go. Yep. Yeah, if you're leaving, that's fine. I'll put these up too later. Yeah, here's 3 to think about. Okay, hopefully you got those down. I'm gonna zoom out a little bit more. I should really give myself bigger spaces to write this stuff. And whatever.
What does the right dash on the bottom epoxide say?
Methyl. Yeah. It's ugly. You're right. So it's also just a methyl group. You can put other stuff there. It doesn't really matter. It doesn't affect the problem. But anyway, methyl. Yeah. Okay. Okay. This one we practiced a whole bunch, so hopefully that's not that bad. I'm going to scroll down now. Hopefully you've got these or screenshotted or something. Here we go. I talked about, okay. Yeah. Yeah, I have a book that I normally pull these things from, but they didn't have any good alcohol ones, so I had to just kind of scrounge around for them. Anyway, this one's kind of nasty. Okay. And now let me write down the monster, which is huge. We're going to start with you always know it's a nasty mechanism problem when it's a huge ass molecule and they give you H3O plus. So let's start drawing out what actually happens. Okay. That covers them.
That last ring is closed, right? That's not
Yes.
just. Okay, cool.
Yeah. Just bad at drawing them out, but you're right. Yeah, I didn't even think about this mechanism problem before writing it. I just found it in a book and thought it looked really nasty. It's kind of a cool problem. Okay. So here we go. Here are the problems. Yeah, I don't think I have any extras. I thought I did, but that's okay. These are some fun ones to think about.
For the last one, when it gives you like H3O plus, so you're supposed to draw the mechanism. So you can like add more stuff than just that, right? Or you literally the only reagent is H3O plus.
Oh, it's just that. Yeah. It's just acid. I think so. I can double check, but when I copied it, I think it was. Yeah. Oh, yeah. Dilute H2SO4 is the reagent. So, in other words, yeah, it's just acid. Get used to it.
You're muted. I don't know if that was intentional.
Yeah, I know. Well, yeah, a friend showed up. That's
Oh,
that's why.
sorry.
Yeah. No, I was giving you a moment to think about it. Yeah. Okay. How about we go through some of these and talk about what they are? And I'm gonna be intelligent this time, and that's not often that happens. How about let me add a layer. Oh Jesus, I don't know how to do this. All right, I might not be good enough. I might not.
Wait, no. So you just need to scroll down, like not scroll, move your mouse down.
All right, it's down.
And then a little more, and then I think you want to go to that one that looks like two things on top of one another. No. It looks like two pieces of paper. I think you wanted to click that.
This thing? No.
Like next to the little up and down chevron thing.
Oh, I found it. Hang on. In my confusion, I figured it out. Okay. Thanks, guys. There's also a new layer in your. Yeah, I bet there's a keyboard shortcut or something. I'm a huge keyboard shortcut person. And all right, thank you.
You could also have gone up to the top where it says File, Edit, View, Image, Layer, and I'm sure the keyboard shortcut is hidden in there somewhere.
You're in fact right. All right. Okay, yeah. Anyway, every week I say that I'm gonna learn how to use this thing, and then I got really good at it last week, and I've been doing really well today, and then yeah. All right. Okay, so what's going on in this first one? Okay, so we have a double bond. We're doing oxymercuration, demercuration. Okay, I didn't need to tell you that. It's not complicated, right? The thing is that we're giving it THF, which does jack shit. Okay, it's irrelevant, right? It's just like literally just a liquid to hold this reaction, so not super relevant, right? Instead, we're going to use the actual alcohol that's on here, and but okay, that means we got to think about it a little bit harder, right? We got to fire up the cylinders. It's going to be a Markovnikov addition, right? So it's going to make an ether in this case, and it's going to make an ether at this carbon, the closer one. Let me draw it extra close, right there. Okay, like real nice and close. It's past 9 p.m., so I don't have to be all formal and nice. Yeah, so okay, it's gonna do this, and well, honestly, do we even need to think about the rest of it that hard? Like, it's gonna make the ether, right? All this carbon stuff is gonna be unaffected. Whenever we do this is not hydroboration, this is oxymercuration. Whenever we do it, and then we do the demercuration, right? You just get rid of whatever garbage is on there and replace it with the hydrogen. Okay, so that's what we're gonna do, and well, you go through it, okay, and maybe we'll be a little bit careful about this, right? We'll think about how much is in our rings. So there's 1, 2, 3, 4, 5, and this oxygen is also going to be part of the ring, so it's a 6-membered ring. If we were trying to make a 6-membered ring, you can forget it because, if we were trying to make a 7-membered ring, it's not going to happen. But this is 6, so well, it's okay. And then, I mean, yeah. There you go, right? That's it. The reason I put this problem up and the reason that this problem is interesting in the first place is because if you put something on carbon 5 here, right? And in fact, if you do put something on there, it'll be a stereo center. So, okay, we gotta actually think about it, right? If we put something on carbon 5 now, well, this is like more complicated, okay? So what will wind up happening is either that we'll get something that goes on here, and this guy either sticks up or this thing sticks down. Okay, and that's harder to tell. But that's like totally the sort of thing that you should, I guess, kind of be ready for, because they can ask you something like this. This example was a little bit simpler. I would totally think about the case where it's not simpler. Okay. How about a mechanism? What's going to happen in this reaction? What is LDA?
It's like a bulky base.
Yeah, exactly. It's a really good base, in fact. Yeah. So in that case, what kind of reaction is it going to do?
A basic epoxide opening.
Okay. Well, yeah, but we do an epoxide opening, it's going to attack the less substituted side, and well, there's a minus, and then there's no way to get rid of that nitrogen now. That's on there for good. But well, it says that it's a mechanism, so we know what the product is going to be. So we don't have to worry about this case, right? We just pretend this doesn't happen. Okay. So in this case, where we're not going to do that kind of epoxide opening, we're going to do something else. So LDA is a really good base. What do really good bases like to do?
Elimination?
Oh, yeah. Yeah, they do. Exactly. So it's going to eliminate, okay? It's going to eliminate this oxygen, this epoxide, right? That's pretty wacky, but no reason it can't, right? So what's going to happen is that this hydrogen is going to come off, okay? So here's LDA, right? This is what it looks like. So it's going to come in. It's going to take that hydrogen, boop, take that off, kick off that oxygen. Okay, now now we got our double bond in this, okay? And I don't need to tell you the rest. Okay. Here we go. Here's an epoxide opening with a cuprate, right? Is it going to attack the more or less substituted side?
Less.
Yeah, it attacks the less substituted side. So less, right? And this is an exercise in stereochemistry, which you can do. Okay. This is like another, like, one of the really common types of problems is that there's like a, I don't know, like a double bond, right? And then you do some reaction on that double bond, and like there's two like crazy things on either side, and you have to figure out what the stereochemistry is at the end. Another kind of one is if you have an epoxide with a whole bunch of stuff on either side, and then you open it, what's going to happen? So this is kind of that sort of thing. It's a common type of problem. So I would, should work this one out. I don't know why I included this one. It's not like overly crazy, but it's totally like a standard question that they'd ask. So hydroboration will make what in this case?
Is it aldehyde? It's like the double bond O with an H.
Exactly.
I don't know what that one's called.
Yep. It'll do it with keto enoltetomerization too. So learn that.
Have you read that as a step?
No, you don't. You don't have to. But, well, if not on this exam, you will inevitably asked about keto enoltetomerization in Orgo 2, if not on this exam. So totally something you should know anyway. Okay, so here we have this guy. It's a lactam if you care about, or I think it's a lactone, whatever, it's the same thing. Okay, and so lithium aluminum deuteride is gonna open it up, right? Because this is strong enough that it can cleave esters. So that's what it's gonna do. Okay. So this thing cleaves the esters. Okay. And well, you should think about what it does when it does so. Okay. So it'll cleave the ester, and then on one side you'll get an aldehyde. Okay, great, but it's in lithium aluminum hydride, so that aldehyde isn't going to last very long. And then what happens to the other side? Well, that too. And it's deuterium, so well, just to piss you off a little bit more, you can use those. Okay. All right. Well, what's going on with this last problem? Well, this one's kind of ugly, but we're just going to protonate somewhere. And you might also notice, well, this whole side of the molecule is totally irrelevant, right? I could have drawn nonsense there and it wouldn't make a difference. So we're not going to worry about that. Instead, it's literally just these two rings that open and they make aldehydes in this alcohol. Okay. So the question is just about where things protonate and deprotonate. Okay. And I now remember, after pulling this problem out of a book pretty blindly, why I like this problem, which is that it is totally about the keto enoltetomerization. Okay. You got to do it like 3 times in this. You got to do it like 2 times in this problem. But it's what it's all about. Okay. So you're going to have to do keto enoltetomerization, and you're going to have to do it 2 times. Okay. That is totally something that you should work out. Okay. Sound good? Everybody feel okay?
Could you quickly finish up the 1-2 problems go before the alkyne with the epoxide?
This one with the epoxide? Yeah, actually, let me write that out. Yeah, let me just write it out because this is like the sort of thing that, oh geez. that's not what I meant to do. Yeah, let me move this thing because this is like a not super helpful thing. Okay, yeah, so oops, I need to do this. Okay. So this thing is gonna attack the less substituted side. So okay. Please let me write. Thank you. There we go. Yeah, so we're gonna come up here. It's gonna attack here. This epoxide is gonna open. Great. We'll protonate it. Sure. I mean, I'm not gonna. All right. Never mind. I will write it. So it'll protonate there. Okay. So nicest way to do this is just draw that bond where the action is happening as a straight line, and then, well, this methyl is still facing the back. There was a hydrogen here. I just didn't bother drawing it in, right? There's a pH here now. And then, well, the rest of these things stay as they were. So it looks like that. Okay.
Thank you. I didn't realize it was that simple.
Yeah, that's it. Yeah. They're hard to keep track of how much stereochemistry there is going on though. Especially because, well, not in this case, but there are some times where they'll like rotate the molecule. Like they'll take this and like they'll take this side of the molecule and they'll like rotate it and they'll be like, oh, what happened? And then you got to figure it out, and that's like a real pain. Yeah.
But whenever you have the opening of an epoxide, it's always just going to keep the stereochemistry with whatever other functional groups are attached.
Yeah.
Okay, cool. Thank you.
Totally will. Yep. Okay. Those were the problems
Also,
that I had.
Can you quickly just draw out the product for the last one with the LiAlD4?
Yeah. So the product is this. That's it.
Thank you.
Yep. Okay. Cool. Well, those are the problems that I had to talk about. I think we've thoroughly exhausted our time, so I even stopped the screen share.